Thank you guys so much for coming to talk to me today about some really important announcements that we have at QTex AI. I'm just going to go ahead and introduce everybody really quick. I am Katie McAnally, your host and content manager at QTex AI. Full disclosure, feeling a little under the weather. That's why this unconventional recording style. And I'm joined by our CEO, Chris Dagger, our COO, Oliver MacDonald, and our software engineer, Caleb Pollock. A few weeks ago, you came to Caleb and I and made an announcement that we would be pivoting our product focus from parts search to schematic review. Let's just talk about what factors led to that decision.
Yeah, I mean, it was pretty much, we looked at what was happening with part search. We looked at where we were, the technology, and kind of said, this is pretty much as good as it needs to be. And it's also not, to be frank, it's not the way to deliver the most value to engineers. Like, it is a way to deliver good value to a certain type of engineer doing R&D, but it's not the most valuable way we can apply the technology. And so Oliver and I kind of got together and said, well, we've wanted to deliver more value and do more with this tech. So what's the next logical step? And it really was pretty much design review and like looking at schematics, analyzing all the connections and saying, okay, these are potential issues before they become hardware issues, before they become like real problems that cause boards to blow up and set on fire and whatever, not work, which happens, as happened to both of us several times in our engineering careers. So we pretty much agreed that was the next step. We'd gotten some feedback saying that it was a useful thing, particularly from some prospective customers and from existing customers. And so we just said, okay, yeah, let's go do that.
And it wasn't some big move in the sense of, oh, now this is something that we hadn't planned for. This is something we'd always planned to move to. Part search was always the core foundation of everything else we planned. We needed to know the data, how to organize it, and how to pull from it as best as possible to then build something like a schematic review where we need to be able to pull on that data and understand its relationship to now a schematic as well as back to what the user wanted. And since we got that user intent to part search, we could now wrap that into schematic. And the goal is to just keep building on top of this technology as time moves forward.
Yeah, I mean, the real foundation of it is the data. And that's what our stance has been since day one, is like, we want to help engineers, and the most effective way to do that is by figuring out how to work with this enormous amount of data, because technical data sheets are huge, they're really complex, there's tons of information in them, and it takes a lot of mental load and a lot of work to really put all the pieces together, especially across data sheets. And so we're super data focused. Like, we want to enable engineers. Oliver and I are hardware engineers, both in our background and at heart. And so we pretty much said, yeah, we want to enable these engineers to do their work more efficiently, but the way we do that is through data.
We started with, like you said, the goal of destroying these massive data sheets. That was our goal to start out with. So you're saying that we haven't necessarily abandoned that goal. We're just kind of expanding on that goal?
Yeah, I mean, we've never really abandoned the goal. We have not abandoned the goal. The goal has always been, how do we help engineers be more efficient, build better products, make less mistakes, have more fun, right? I mean, engineering is a hard job, but it's a lot of fun because you get to play with stuff and build stuff, and you're literally designing and creating the built world. Like, everybody lives in the built world, but not everybody gets to create it. And that's the really exciting thing about engineering. But yeah, the data sheets are really the problem. And so it's not that we've shifted focus, it's that we've essentially realigned to, we want to help engineers do the things they want to do instead of like doing the mundane work, the busy work, the stuff that is really error prone and takes tons of time and isn't what they actually enjoy doing. I mean, we haven't talked to anyone who's like, yeah, I really love reading data sheets. Like, that's just all I do all day, every day. I read data sheets and I love it. That's all I want to do. I wake up and I read them because it's fun. I read them before I go to bed because that's just like light nighttime reading, Nobody says that.
I'm sure those people do exist, but yeah, they're probably rare.
Okay, I'll be honest. Occasionally I've seen a part and been like, oh, I want to skim this data sheet, but I've never been like, yeah, I really want to dig into that.
I mean, because the part's more interesting than the data sheet. It's the thought of, actually, there's a part we found a few months back that was this lightning detector. And we pulled up the data sheet not because we wanted to read it, but we were like, we want to build something with this.
Yeah.
We want to throw together a lightning detector to have in the office and call it a day.
Yeah, Caleb had a cool idea for that actually.
Oh, yeah, yeah. It was just a light that would turn on when there was lightning.
I mean, yeah,
That was what it
that was the idea. Yeah, but you were like, it's got to be like this really, like well made wood board and just a light, literally just a light. It was kind of funny that it's like, all right, we've got this really complicated, fancy sensor, and all it does is turn on a light.
Yeah, I mean,
With like apparently, according to the data sheet and according to our system, like what 50% accuracy.
Not even. I think if it was within a kilometer, it was like 40%.
So,
But the chip wasn't too expensive, so we might build it at some point.
I think I was walking into the office when you guys were having
Yeah.
this conversation. And what I said was, why? And the answer was like, you don't get it. You're not an engineer, Katie.
sometimes just kind of fun to mess around. I mean, like if you look at Bell Labs, right, that's pretty much what they paid the engineers to do, is just mess around. And as a result, we got telephone, internet, transistors and semiconductors, like all of these things, just from engineers playing around and having fun. So like that's kind of part of the process.
Totally. It's allowing this conversation to take place from 8 miles apart. So that's pretty cool too. Technology. When you are talking to people who have been invested in the company and might be willing to invest in the company now, how are you explaining moving into schematic review as far as value proposition?
So our thesis hasn't really changed that much. It's kind of gotten refined, but it hasn't really changed. Like I said, we always have been on this mission to empower engineers and enable them to build better products faster. But the thesis has kind of refined as we've experimented and gathered data and also built out our products, which is essentially engineering is really hard to scale. And like this isn't news to engineers. It takes 4 to 6 years to train, on average, to train a new engineer. And then even once they've been trained, right, they have a college degree, to actually gain industry experience, become a good engineer takes even more time. So maybe we're talking 10 years to have a really productive engineer. I'm not saying that's a problem, but when design complexity goes like this and the engineering workforce goes like this, there's obviously a gap, right? Like there's just a fundamental mismatch. And Oliver, you've got like actual numbers on like the workforce shortage, right?
Yeah, so I want to say just for 2024 alone, there were about 17,000 open jobs, or jobs that were opened in the market for just electronics engineers. Not all engineers across the board, just electronics. This was just in the US, and the US alone that year only graduated 11,000 new electrical engineers. So that leaves about 6,000 unfilled spaces. And as time goes on, we're actually seeing a decrease in the number of electrical engineers or those going into the field over time. I want to say it's 1998 to 2020. We've seen a drop from 1.1% of students going to electrical down to 0.9%. So overall, we're actually seeing a decrease in this field, which is also noted as one of, if not the most difficult engineering fields to go into. So it's a very interesting game to play of how do we empower this now decreasing workforce in an industry that's booming right now between IoT, smart cars, new phones every year. NVIDIA announced that they're doing new chips every year. How are we trying to fill these gaps when people aren't interested, or a majority of people aren't interested in just being a part of this field in the first place?
Yeah. And that's really where our thesis kind of refinement comes from. It's essentially that the future of engineering is computer driven. And that's not saying we're replacing engineers, because we're engineers and we love engineering. Just like what we're seeing now with code, engineering is actually like 20 years behind that, right? So Claude Code is amazing, but engineering still uses manual checks. It still uses all of these things that rely on somebody being up late at night because there's a deadline and they've got to check all these different connections and all the wires and read through all the data sheets and piece it all together to figure out if something's wrong, and you're gonna let the magic smoke out of the chip. That's not scalable. Like we're in a workforce shortage. We're not having enough graduates. Enrollment is declining. So our thesis is essentially computers are going to drive design and humans are going to set the spec and check it, just like with the shift we're seeing now in code. And that's not saying that every design is going to be done by a computer.
Humans are the creatives behind it. Humans need to come up with the idea, come up with the purpose, understand the environment where a product's being applied, and pull the specifications from that, as well as pull specifications from those potential customers that don't always know what they want, or you need to dig into to truly know what they want. And that's always going to be a human job. But some of the more offhand work, the not fun work, the tedious work, that if we can offload some of that, decrease number of design cycles, we can help engineers get those products out there with the existing workforce and its growth, and be able to keep up with really demand for the new just society.
Exactly. Yeah. Why can't a computer do a first pass, right? A first draft, and then check the work and give a report to a human to actually review? Why can't a computer do things like signal integrity, calculating temperature rise on a net because you've got a high power connection? Like, these are things that a computer can do, and we just need a human to check, right? The human can do the really high intensity creative work that needs a human, but the majority of work, to be honest, can be automated. And so our thesis, essentially, just to restate it, computers are going to do the majority of the work, and humans are going to do the creative stuff, the hard stuff, the fun stuff. And that's pretty much it. And that's how we're going to fill that gap.
So you mentioned a few times throughout this conversation capability that this technology is going to have to stop fires, both literally and I think metaphorically. I want to hear the stories behind the fires. What is your guys' worst, I should have had this product to check this design before I connected it, stories?
My worst design, I was so rushed working on a power supply for a robot. It needed to have multiple batteries, hot swappable, high current, high voltage. It ended up, the three of us are all worked on this kind of together, but I did the core design for the circuit board. We all know how it went, which is that it didn't work. Because we needed it to be compact and we needed it to be high power density and low loss, mobile robotics.
Needed is kind of...
Well, it did have some pretty tight requirements. It was a mobile robotics application, so it had to be dense because the robot wasn't infinitely big, efficient. Anyway, so like we went with some exotic parts. Like we went with some like relatively new gallium nitride MOSFETs.
Oh, the MOSFETs.
We went with PM bus hot swap controllers. 3 channels on everything. We went with hot swappable buck boost converter modules because, of course, right, like the requirements might change midway through development, and so we wanted to have it so it was like somewhat modular. We got everything put together. Like we got the design made. Oliver and I reviewed the design. We read through all the data sheets, and we missed something. Honestly, I don't think we still are not entirely sure.
We're using the new system to figure out what we missed, actually.
Exactly. Yeah, we're going to run it through. Mm-hmm. But like we plugged it in and it didn't work. And so we started probing around, and then all of a sudden some of those gallium nitride MOSFETs, which were like, I don't know, $5 each, and we had probably 35 of them on this board, they started smoking and popping. And by the way, these things are like chip scale, so they're like 2 by 3 millimeters and just like minuscule. Then we start like unplugging everything frantically, and we're like trying to figure out what went wrong, tracing through the schematic, still can't figure it out. Eventually we just went with like a couple of relays and some modules off of Amazon, and it kind of worked, but like not really well. So I think it almost started a fire, not quite started a fire.
In my case, probably the funniest fire that I started. I want to say this is actually only the second year of my engineering degree. This is actually right before I got hired on as a research and development engineer, but on actually that same project, but before Chris had joined it, I was the lead electrical engineer, had to redesign the entire schematic for the robot as a whole. So beyond just the PCB board, all different components connecting. And somewhere, somehow, I managed to wire in what's called a ground loop, meaning that all your grounds connect, where all your power goes connects in some sort of literal loop. So power, if you think of the like meme of like someone plugging a power strip into itself, that's effectively what I did with the grounds. And that's really bad because it means your power doesn't actually leave when it should. So I'm there working late at night on this robot. One of the other students on the team is working with me. And next thing we knew, things started catching smoke. And to this day, we still don't know what the hell we had wired into a ground loop, where our circuit had spun around. But we just had to throw more wire in, because the nice thing with wire is it does add a resistance, which means it helps decrease current in the system. And so we just added a ton of wire into the system until it stopped catching on fire because we had to get this thing testing the next day.
And by the way, this other guy Oliver's talking about, he now has an electrical engineering PhD and works as a robotics engineer.
Yes.
So if that tells you anything about the current state of robotics.
Yeah, we were both just looking at it in awe. He didn't know where the hell I had put a ground loop in. I didn't know. I, at that point, was still unsure what the hell a ground loop was. I'm like, wait, I fundamentally understand what this is, but I don't know where I put it or that was the thing I had to be concerned about in this system. And yeah, that one, we melted a few wires that day. No full fire, but a lot of replaced wire for that. Any fires on your end, Caleb?
I just kind of like break other people's stuff. I kept plugging in stuff like when I didn't realize the power was on, and then I'd plug it in the wrong way and it'd break.
Fair enough.
But that's about it.
I mean, that's a lot of software engineering. Not if you're working with embedded, is you're having to do a bit of the software, but also a bit of the hardware and connections.
So the search tool, the first tool that we made, was about retrieving data. Like, that's difficult for a human to do. Like, it's pretty straightforward. It really is just about data retrieval, right? So am I right in thinking that schematic review is much more complex? And how does the technology kind of evolve to handle that complexity shift?
I'll kind of touch on data retrieval and reading a data sheet and then talk about design review. It's not a simple problem. Like, it sounds like a simple problem, right? You can hit Control F or Command F in a PDF document and do a keyword search. That doesn't really work for a lot of reasons, right? One of them is you need to understand the semantic intent behind the actual words, which is what language models are really good at. But you also need to understand the structure of the document, because two things can be really semantically similar, but completely irrelevant to each other in the actual context of the document. For instance, if I ask about packaging, am I referring to the actual packaging of a microchip and whether it's in like a SOT23 or a DIP package or whatever? Or am I referring to bulk packaging and is it tape and reel? How do I order this in bulk? Both of those really semantically similar, but fundamentally different within a data sheet. And so understanding the structure of a data sheet is really important. And traditional RAG just doesn't really cut it because it's trained on the entirety of knowledge everywhere. And so like embedding models are trained on the entirety of knowledge everywhere. But electrical engineering is really specific and nuanced. All engineering is. And so we actually had to build our own agentic storage and retrieval system in order to get really good accuracy. And it's like over 98% accuracy on retrieval and question answering from our testing, which is excellent. I mean, we're super happy with that. Our customers are really quite happy with that. And that's like the kind of thing that engineers need, right? Engineers are not willing to accept a mistake. They're not willing to accept a hallucination that ruins their design. So it really needs to be 98% or better.
So you're saying that it's not straightforward.
Short answer, it's not straightforward because these documents are complicated and technical, and RAG strategies just don't really work for those kinds of documents.
I mean, even just for an example, I was working with one of my students this last Monday on trying to figure out what chip he could use for one of his designs, and we had to look at what's called the thermal derating curve. Pretty much after a certain temperature, the chip starts to be less efficient. And we had one document that gave us the room temperature for derating, or what the temperature of the ambient air around the chip was, and the temperature of the board. One that only gave us the room, another data sheet that only gave us the board. Data was spread all over the place in multiple different parts. And there was a lot of walking through with that student of, okay, we need to look here for this. Now we need to look over here for this information. And on this third place in this third data sheet for this information. And one of them didn't even have the information. We just had to say, well, based on these other specifications, it's probably around here. But it's difficult to have to jump around so many times, especially when you're trying to get something out within that hour and trying to make sure you make the best choice when you're faced with so much data.
Mm-hmm.
So that being said, does the new tool require more complex reasoning, or is it similar?
It does require more complex reasoning. So a lot of people look at LLMs and say, oh, well, they're thinking, they're reasoning. Not really, right? I mean, they sort of talk to themselves, but it's not quite so simple. And we actually ended up having to build some pretty complex agent harnesses, which essentially are just like the environment that the AI agent operates in and the tools it has access to. And so really tuning those and making them all kind of work together as a collaborative system, because design review is really complicated in general, right? You have to do calculations, you have to read documents, you've got to connect all the dots, you've got to make sure you didn't miss anything, you've got to check interactions you didn't even think you had to check. And so it's one, a huge amount of context. So for anybody thinking, oh, well, Gemini has a million token context window, that's not enough. Additionally, long context conversations derail LLMs. So they're not actually good when you start talking like, oh, okay, well, it's a million tokens context. I've only got 800,000 tokens. I'm fine. You're not fine. So context management or context engineering is really important. The agent harness is really important. And we had to essentially design all of these around a mathematically rigorous and grounded approach to the design review process. Because the other piece, which I actually didn't even touch on, is that a schematic is a really weird thing. Like in a theoretical sense, it's this thing called a hypergraph, which I'm not going to get into, but like you can look it up on Wikipedia. So schematics are hard to work with, not only because they're this like complex structure, but also because everything gets messy because physics is real and the real world is messy. And so taking all that into account beyond just like, oh, an abstract thing, right? Code is very abstract. So LLMs are great at working with it, but hardware is not. Hardware is very physical and works in the real world. So reviewing a design that's supposed to work in the real world is really pretty hard. So it's a harder problem to really answer the question directly.
Okay, you mentioned super briefly about engineers hating and not accepting hallucination. So let's talk about hallucination and how that applies to the new schematic review tool. Are we saying that this AI is just 100% infallible and accurate 100% of the time?
I'm pretty sure if we said that, we could go raise like $20 billion, because I think that's the last round Anthropic raised, 20 or 30 billion. So no is the answer. We are not saying that our system is 100% accurate, completely infallible. The way we get around that is we rely on systems that are traceable. We rely on systems that are grounded in data, that we validated the retrieval and the reasoning approach on, so we know the accuracy and it's acceptable to us in terms of the risk, the hallucination risk, and everything is cited. So if we're citing, oh, hey, this microchip doesn't have appropriate circuitry internally for this configuration of pin, right? Like let's say you've got a serial communication bus and you need it to operate at a certain speed and the microchip doesn't support that. Okay, well, that's grounded in the data sheet. So we'll tell you exactly the page number of the section and give you like a brief excerpt from the data sheet saying this is why the review agent raises this as an issue. And, you know, like I said at the beginning of the recording, we're not replacing engineers. We're just doing the annoying parts of the job. And so we're essentially saying like, okay, hey, these are the things that we found that you probably want to take a look at. And this is why. And here's, by the way, the source material you can go look at to validate whether or not we either completely blew it, because we've seen a couple examples of that, right? We're not 100% accurate, but most of the time it's pretty accurate and it's pretty good. So no, it's not 100% accurate, but the way we get around that is with rigorous citations and what we like to call explainable generative design. We're not quite at generative design yet, but our whole process is explainable because we can look through every single call, every single thought signature, and look at exactly how the agent got to the conclusion that it did for every single issue that it raises. So it's really about trust and citation and making sure that we give engineers the information and the context that they need in order to feel confident in the results.
I mean, it really all comes down to transparency.
Mm-hmm.
It's a matter of making sure that if an engineer has a question about how we got to an answer, the system can answer that question. It's that they can track every step, as Chris said, to know why a decision was made and why it's important to them. Because we, as engineers, work with black boxes sometimes too much. Electricity as its own is a bit of a black box when trying to work with it. So the more we can make transparent for them, not only is it more trustworthy for these engineers, but it also helps everyone. It helps our own design process, it helps theirs, and it can help flag things that might not ever be considered or looked at if you work with an entirely black box system.
Mm-hmm.
When the system tells you, here's what you need to fix, but with no explanation of why, or with no details of how it got to that conclusion, it's not that useful, because at that point, it comes back onto you to have to go find all that information to verify what the system told you, rather than having everything presented for you up front for you to be able to make that decision.
And at that point, you may as well review it yourself.
Yeah.
How does the last year spent on the datasheet problem set QTex up for success in this new endeavor of schematic review?
I mean, I think either of us could talk about that. Well, any of us could talk about that. But I think that the last year spent on the data sheets kind of gave us two things. The first is a really strong foundation in the data and understanding of both how to build really robust agents that work well with data sheets and that can understand them. Because like when you get a PDF, as an example, when you get a PDF that's a financial report from the last quarter for some corporation and you put it into ChatGPT, it's fine. It's not a big deal. It's not going to be perfectly accurate. It's going to hallucinate a fair amount because long documents, these things still struggle with if you just give it to it all at once. But generally speaking, it's not going to have a hard time reading the document. It might not pick out exactly the information you want, but it won't have a hard time reading the document. When you've got a PDF that's scanned and blotchy because it's like a scan of a scan of a scan and it's crooked of a part from 1985, it's pretty much hopeless if you just upload it directly. So the systems that we built are robust to things like that. They're really good with long documents. To kind of touch on context window again, Gemini has a 1 million token context window, and that's about 1,000-page PDF, or 1,000 total pages of PDFs. But we regularly work with like 2,000, 5,000, 20,000 page PDFs, and that's not an issue for us. So that first year pretty much enabled us to be able to say, yeah, we can take more or less any PDF about a technical data sheet for a microchip and actually break it down into a structure that these LLMs can understand and that we can give to an agent. The second piece is really how do we actually present that to the user, right? And how do we build trust with the user? And so our first product, the conversational search engine and design assistant, it really gave us a lot of experience with how do we make something that a user feels comfortable talking to and that they trust, and how do we show them that it's actually doing something instead of just coming up with something, like coming up with some random answer and hallucinating. So I would say those are really the two things that first year of just working on data sheets and search and understanding the technical documents really did for us.
Yeah, that is making me think about how I didn't really come up with very many like operations and marketing questions. So that's why Chris has been dominating this conversation. Oliver, can you talk about it from a marketing and kind of operations perspective?
Engineers are not easy people to find. Dare I say easy creatures to find, because Hideaway at our houses working on God knows what chaotic project that has probably put us on a list somewhere, someplace, because it's just fun to work on different engineering projects, regardless of your discipline. I know many mechanicals, electricals, software engineers, we all have different projects that we tend to work on our spare time. But figuring out how to find those communities and integrate with those communities, there's been a lot of work to just get that in place. And now having a footing in those communities, it gives us a bit more space to start testing out a bit more direct messaging, a bit more direct content, and understanding really what is resonating with these spaces, with these professional engineers who are also hobbyists, and building trust through that manner to build trust with larger companies at the same time. And then operation-wise, luckily that hasn't really changed much in this. It's outside of changing pitch decks and messaging for investors in that, the day-to-day stays pretty similar in reviewing finances, understanding our own security as well as the security of our platform and our customers' data, handling just in the office technology we need. That tends to be pretty similar because we built a system that was meant to scale, not just in our product, but in the entire structure of the company. We built so that as we grow, we can grow our process with us very seamlessly as well, so that we don't have these drastic changes if something has to change. It's just, operations keeps going as it is, just expands or changes messaging, and we just keep moving from that regard.
Who is your ideal customer for this product? Is it somebody who's just doing their own schematics for hobbyist purposes, or you're looking for huge Fortune 500 companies, or who is the ideal person that if you could sign with them tomorrow, what would that look like?
A customer is really going to be Fortune 500 and Fortune 100 companies where they have big hardware teams. Companies like Apple, Google, Microsoft, less so Microsoft, but they do, like they make Xbox and the Surface. These kinds of companies go through tons of prototypes. They're constantly iterating, constantly designing stuff. So those are really the ideal companies. They'll see probably the most value out of this. But on the other hand, startups and mid-sized companies that are designing hardware are also, in another sense, a very ideal customer because they have smaller teams. They've got the same timelines as these giant companies. They're under, in a lot of ways, more pressure to deliver and ship than any other company. So the value proposition for something like design review for an engineering manager in a company with maybe 50 to 100 or so engineers, or 250 engineers, is pretty clear if their engineers are making fewer mistakes, getting products out the door faster, and overall can actually design a better product, which makes their offering more competitive and more compelling for their customers.
We really want to work with those engineer managers who are realistically engineers themselves, who have lived the problem, who are in an R&D space, like Chris said, are developing new technologies either for Fortune 500s or managing a team of even 1 or 2 engineers at a startup to mid-sized company, where at the end of the day, their goal is to get a new product designed quickly in as few iterations as possible to get it out the door and start selling, especially in a day and age where hardware is really struggling right now to get anything out the door because it's hard to develop something physical and get that in place. So if we can help really those engineering managers who are struggling to get product out the door, turn their cycles around and start being able to produce the technology they want to produce, but within the timeline that's been forced on them, that's where we see the most value for our customers.
Is there anything else that you guys would think is of value that you'd like to add to the conversation? As has been well established, I am not an engineer, and these are the questions I've come up with that I was curious about, but I'm sure that I've missed something.
We're not done. Like that probably sounds kind of obvious, but design review is not it, right? Like that's not the end goal. Like we said earlier, we're really on a mission to help engineers be more productive in all kinds of ways that they work. Electrical engineers right now, for sure, but we've certainly got our eye on a couple of other engineering disciplines that have similar bottlenecks. Design review especially is not the end, and electrical engineering is not the end. So there's a lot more that we want to do with this, and there's a long way to run.
The sky's the limit.
Ways. Well, actually, no. Space is the limit. Engineers build stuff that goes into space. So the infinite cosmos in many ways is the limit.
The edge of our entire galaxy. That theoretically fictional, but yet not fictional, like drop into the abyss.
Oh, we have the observed universe.
Oh, yeah.
So there's the edge of the observed universe.
Yes.
Beyond that, we have no way of knowing what's there. So.
Yep.
Yeah.